Hi. So let's talk about self-supervised learning. So far, we were playing in the realm of supervised learning. But what we want to talk about now is self-supervised learning, also known as sometimes unsupervised learning. So let's ask a provocative question. Let's ask, what does a baby need to know to learn that if they, let's say, drop glass, let's say a glass bottle, it'll break? Does it need to know what the glass bottle looks like and what the broken glass looks like, let's say 10 different or 100 different samples of that? Or do they learn this, that if they drop this bottle made of glass, it will break, by interacting with nature, by somehow understanding this information, this knowledge, even without breaking 10 glasses? How do they do it? So what we've been doing till now is supervised learning, where let's say we have a data set such as ImageNet, and ImageNet is a data set of 1 million training images collected by Professor Feifeli from Stanford. And this is one of the reasons which ushered in this age of deep learning, because this was the first massive data set collected and labeled, right? So this data set has 1 million training images and 1,000 classes. And those classes can be a cat, a dog, a cow, a flower, and so on. So you have these images, and for each of these images, we have, provided labels. But the images and labels, so let's say label data, which constitutes supervised learning, where we supervise the model how to learn, only constitutes the tip of the iceberg. It's only a little part of the entire data present in our world. The rest of the data, the dark knowledge, the dark data, is essentially, present everywhere. We have, let's say, billions of YouTube videos which do not really have labels, but they're just, they're just videos. We may have, let's say, trillions of photos in all our phones put together. Again, they are not labeled, they're just photos. Now the question we want to ask is, can we do something with that? Can we learn a model from that? Can we somehow learn that knowledge? And Jan has this very interesting analogy. He says that think of machine learning as this cake, where supervised learning is only your icing, right? It's this very thin layer, because very little of our data is actually labeled. It's very important, it's very sweet and tasty, but it's still a very small part of what we have available. The true power lies in this cake, which is the unsupervised or the self-supervised, let's say, regime, where we play in that regime, self-supervised. And this cherry is actually RL, because the signal that comes from RL is very weak, it's very sparse, and we only use it to, let's say, amplify existing behaviors of the model. And we'll talk more about it in the last week when we talk about post-training LLMs. But for now, we need to kind of understand that the majority of the information, the power of machine learning, lies in this unsupervised learning. And this is what we're going to learn in the next few, let's say, videos. So the question we ask is, how can machine learn like humans from this unlabeled experience? And the good news is that yes, we can learn, but why can we do that, right? So for that, we have this so-called manifold hypothesis. It's just a fancy word, which basically means that, our true data lies in this low dimensional manifold in this high dimensional space. Meaning, let's say we see this, static noise that we have here, and let's say this is an image of size 1024 cross 1024. Yeah, I know it doesn't look square, but let's just assume for understanding that this is a square image of size 1024 cross 1024. So how many pixels in this image? 1024 cross 1024 is about 1 million pixels. So we have about 1 million pixels in this image. Now, if we want to do, let's say, machine learning on this, what do? We convert it into a vector, and then we can put it into a fully connected in a, or something like that. So how big will this vector be? This vector will have about 1,000,000 dimensions, right? So it's 1 with 6 zeros. Now, how many such vectors are there? How many such distinct vectors are there? Let's assume the pixels here can only assume two values, white or black, right? So it's just a monochrome image that we're making. And the question we want to ask is, if we can only, let's say, make these monochrome images, how many such distinct vectors are there of size 1,000,000? The answer, of course, since each pixel can take two values, it's 2 to the power 1,000,000. Yeah, so these many different vectors we can create. And forget about this 2 to the power 1,000,000, because this is such a huge number that we cannot fathom, we cannot imagine this in our heads. Let's say our image is smaller. Let's say our image is 10 cross 10. Then this 10 cross 10, how big will that vector be? It will be this 100 dimensional vector. Again, the same setting. Let's say the pixels can just be black or white, right? So it can either be 1 or it can be 0. So how many such distinct vectors? Each pixel can take two values, right? And then how many such pixels? 100. So it's 2 to the power 100. And now this 2 to the power 100 is also such a crazy number that if you kind of try to sample all of this, it will probably take forever. Yeah. So the point that I'm trying to make is that this space is really huge. Even for this 10 cross 10 image, if you're not able to sample all of them, because my hypothesis here is if we can sample all of them, then some of them will look like something, right? Some of them will look like faces. Some of them will look like, I don't know, the sun, the moon, the trees. But this space is so huge that you almost never get a face. You know, the set of all valid images that look like faces or toys or trees or flowers is this tiny island in this vast ocean of noise. And that is this insight that I want you to remember. If we were to randomly sample in this high dimensional space, the probability of you getting a valid image is close to 0. Yeah, because this space is so high. But your data, your say manifold, the distribution of natural images is this tiny island in this vast sea of noise. Let me explain this to you with an analogy, right? Let's say the data that we have is this straight line and we've drawn this on a piece of paper. And then we take this piece of paper and we crumple it. We crumple and make a ball out of it. And now our data, the space that this true data lives in, is 3D. In 3D, the start and end points of the line may be close to each other, and the line may actually look, this crooked line, this crumpled line, which looks like actually a 3D line. But the underlying data is actually this two-dimensional line. It lies on this two-dimensional plane, but we have projected it onto this three-dimensional ball. Much like our images. So let's say images of faces, right? They lie on a lower dimensional space, but we have now projected it onto that image space of size 1024 cross 1024. So that 1,000,000 dimensional vector, that 1,000,000 dimensional image is not really the data, let's say, dimensionality. The data dimensionality is lesser. In this case, the data dimensionality is 2, but then we have projected it into this 3D space. Similarly, our data dimensionality, the data lives on a lower dimensional manifold in that high dimensional space. And the job of this unsupervised learning in this deep learning context is to uncrumple, to flatten the manifold so that we can understand its true structure. Let me explain this further. Let's do this for images of faces, right? So the face manifold. Our face has about 42 muscles. It has a bone structure. There is maybe lighting, pose of the face, age, ethnicity, appearance, expression, background, shadow. But if you keep counting all these variables, maybe we get to, let's say, 100, maybe 200. but not more than that. So the underlying data distribution for faces, for example, here we only change one of those axis, right? When we have, let's say, our vector, we have a million because our images are 1024 cross 1024. So our vector, we have these 1,000 dimensions, sorry, a million dimensions, so these million axes, but we are changing only that one axis, right? In that true data distribution, we let's say only have 100 dimensions, and one of them is, let's say, age. And here we are keeping everything constant, or trying to at least, and we are only changing the age. In this case, we are only changing, let's say, the size of our eyes, and we are trying to keep everything else constant. Here we are trying to change the perspective, the pose of the face. Here we are trying to change just the mood. Yeah, and then you can try to, again, these are essentially the axis of the true distribution of data. So the true distribution, probably these are the semantically meaningful dimensions, the low dimensions of data, but then the images that we have created from these are very high. And the question we are asking is, how do we try and kind of understand these real, let's say, axis of our data, the data that lies on a lower dimensional manifold? Yeah, so images actually lie on a lower dimensional manifold. And what happens when we start to kind of go away from the manifold? Imagine, like we are in 3D, and in that 3D, let's say this is, let's say, a cube, and inside this 3D there is some surface, right? And this surface, let's say, is the manifold of our true data. But what happens when we go a little bit away from that manifold? Then we start to get images which then don't look like our data. Then images that, look like this, and look like this, and look like this, because they are just outside the manifold of our data. And then when we go really further away, it starts to look like noise. It doesn't look like any natural image. And this high dimension is a very interesting space, which we will talk about later in our sessions. So the only thing that you need to remember is, what we want to do is, we want to kind of try and understand what is that low dimensional manifold where that data lives. Because the observation that we have of that data is this high dimensional space. Let's say the observation is an image through a camera. The observation is, let's say, a sound wave through a microphone. The observation is, let's say, a paragraph of text. So that is our observation, which is a high dimensional object. But the underlying machinery which creates that data usually lives on a much lower dimensional manifold, because that image is a million dimensional, but that underlying manifold which generates that image is probably 100 dimensional. Yeah, so that is what we are trying to understand, how to get to that generation, let's say, that true manifold of that data, and how to do that in an unsupervised way, how to do that without, let's say, labels. And this is the topic for our next videos.